Topic 14. Today we'll cover the cascade compensator design using the root locus. In this case today, we will deal with the transient and the steady state compensation. So, the topic learning objectives. By the end of this topic, you'll be able to explain the concept behind the cascade compensation, explain the reasoning behind addressing the transient response. Last time, what was that? Steady state error. Today, transient response. Last time, what was that? PI and lag compensation. This time, PD and lead compensation. Both of which using the root locus. And we design, instead of the PI, we design a PD compensator, as well as instead of lag compensator, we designed the lead compensator. Okay? Using the root locus. Here, we do this to satisfy the transient response criteria that cannot be satisfied by a gain K alone. We also design PID as well as lead lag compensators to simultaneously address various transient and steady state error criteria. If time permit, I may talk about a little bit of the notch filter and 2 video clips that you have to watch yourself later. And these are not on exam, however, related to the exam. So please, study a little bit yourself. Okay, those are bonus slides. Okay, so let's look at the PD compensator again. We were doing PI last time. What was the PI doing? Eliminating the steady state error. What was lead compensator what was the lead compensator doing? To improve the steady state error response. Unlike the PI system, the PD system deals with the transient response. You want to improve your transient response. Last time, we were, without appreciably changing this too much, we wanted to improve the steady state error. So we want to have something like that. So this is PI, this is K. Today, okay. This is okay. However, this is not good. For some system, we may have to make it like this. How do you change it? We use the PD system or phase lead system. Okay? Now, major difference is last time for designing PI controller as well as lag controller, we had this design point established through the proportional gain K. We set the design point based on the zeta value, and therefore we had this line. We had this design point for theta equals something. That was, and then if this intersects with your locus, this was your design point. And you didn't want to change this much. After putting together this PI controller by putting the pole at the origin and then 0 near the origin, remember? Through the pole 0 cancellation, although this was increase the type of the system, type 0 to type 1, it acts as if there was just original second order system, thereby not changing the design point. It changed it a little bit. But it eliminated the steady state error. That was what we did last time. Yeah? You follow what I say, 90%. Give me 2 claps. Up. Thank you. Now, D case is different. It may cause root locus to pass through design point regions complex plane. Initially, it would not. That means you will change design point significantly. By doing it, you touch this part, not this part. This part can be changed also, but it depends on how you design it. You can affect this, you can not affect it, but basically what you want to change is this part, okay? All right, how do we do it? We include a proportional, another one. So PI controller, the integrator alone was not used because of the stability issue, remember? So we added P, so it becomes PI controller. Same for the D controller. D controller alone is not used because it amplifies noise. And I'm not going to explain much. You would understand this better when you learn the body diagram and the frequency response analysis later part, like of this month, okay? But anyway, the bottom line is pure differentiation may amplify noise. Therefore, we use PD instead of D alone. All right, PD. So that's PD. P, K, and this S plus Z. So we have to add a 0 somewhere. And you have to find this location. Okay? And the method is slightly different from that of the PI controller. So let's look at this example. Uncompensated means a K, okay? It's not exactly uncompensated because you have K, you modify your K. It is a P control, but in this textbook, it is saying uncompensated. So it's different textbook uses different wording. Okay, so that's your system. With the value, you increase the K from this point and then go, and then your roots has moved. Your closed loop pole has moved here, and then of course it is symmetric about the real axis. You will have another one, so you don't really worry about it, okay? Because it's symmetric exactly. So just one. And we have the design point, which is zeta is 0.4, therefore the angle is 113.6 degree. Okay. The cross-sectional area here, the crossing point, that's your design point with the K. Now, let's add PD. PD means you are adding a 0 to the system. Where do you have the 0? Aha, you have the 0 to system. However, you put your 0 at this pole so that you can have this pole 0 cancellation. So the system exactly working exactly like two second order system is a third order. So that's how it works. Now, design point has been dramatically modified. And you don't always need to have this exact pole 0 cancellation. You may have a little bit like, you may, determine to put your zeros in a little bit different locations. So there is no exact pole 0 cancellation, right? 3, 2, just similar, not exactly the same. 4, 5, not exactly the same, right? But you have kind of similar. So, the reason we do this is to meet the multiple transient criteria. You want to have, fulfill the overshoot, you want to fulfill the settling time, peak time. There are several things, right? So you, either of this, maybe one of this, or none of this could fulfill the requirement, okay? So you have several different ways to achieve the goal for the control. So look at this step response. Initial uncompensated, that's with the K alone. But by adding this PD controller here, where you put your 0 at S equals -2, this one, you added 0 at -3, this one at -4. They are similar, but a little bit different. But interestingly, also, the steady state, even the steady state error response has been improved. Okay. So let's practice. 16% overshoot. That's your requirement. You have this system. You don't know what control you have. You probably have to use a PD controller because you want to have 60% overshoot. Most likely, you may, if you run this thing with the K, the proportional gain alone, you may not have the 16% overshoot. No, I'm sorry. No, 16% overshoot is set. So zeta, it is set. So the theta, in this case, gamma, right? Gamma is more precise. That's what we used, gamma. So that was a set. But what we want to do, which is different from the proportional control alone, is to reduce the settling time by threefold. Okay? So if the settling time that you obtained using the proportional control alone, P control alone, was, say, 3 seconds, you want to have it 1 second instead of 3, using the PD controller. You understand? Okay, how do you do this? Let's see first. Let's start from what we know, 16% overshoot, from which we can deduce the zeta value, that is a 0.5. And TS new is TS all divided by 3. From that requirement, settling time by 3x, you have to reduce. Okay, so P controller alone, and this is your trend line, okay, zeta, and you can find this trend line, it's not called trend line, but anyway, you have this angle that is set by the requirement again for the zeta equals 0.5. In order to have this design point here and here, K has to be 43, and pores are, one is here, that is 7 point something, so that's non-dominant. Dominant pores are here. Dominant pores are those that are closer to the j omega axis. So that's negative 1.2 plus minus j2. That's that point, okay. Okay, now what? Okay, so TS old is 4 over sigma. You remember? TS, the settling time, is 4 over zeta omega n, and zeta omega n is sigma. Sigma is that point, right? So in this case, this old means only with the K, the proportional controller, where K is 43. Then your sigma is 1.2, 1.2050, okay? So you can find the settling time from this system when you use the proportional controller alone, right? So that's 3.3 seconds. Give me thumbs up if you're with me. Thank you. So with that, so we have all the information. We got zeta, that's the design requirement, from which we get the settling time. Okay? So that is, in this textbook, it is uncompensated settling time, old settling time. What do we want? We want to divide this by 3. That's what we want, okay? That means you change the settling time. In order to change the settling time, you need to change what? Transient response. In order to modify, improve transient response, you have to apply PD controller or phase lead controller. Okay? So we have to find a new design point, okay, for the PD controller first. So new design point, yeah, T S new is 3 over 3. That's about 1.11 second. So that is our new settling time. New settling time. Since we now know the new settling time is 4 over sigma new. New sigma. That is 3.6. Correct? If sigma is 3.6, since sigma is zeta omega n, and we know sigma, we know zeta, therefore we can calculate omega n. What is omega n? 3.6 divided by 0.5, that is 7.14 radian per second. That's your new omega n. Not old omega n, new. So we have to find that design point in order to achieve that design point from old move to that new design point, you have to use a PD controller. Okay? So we know sigma, omega n, therefore we know also omega d. Omega d is omega n times square root 1 minus zeta square, which means that this is, what was that, sigma, new sigma, the design point, 3.6. So that should be negative 3.6. And omega d, 6.17. This should be 6.17J. Okay? So what's our design point? Again, that's your requirement. That's the angle, asymptotic angle, not exactly, that's not asymptotic angle. I would say that's trend angle. That's 0.5, that is a zeta. And new sigma, 3.6. So that's your trend line for sigma. And another trend line for omega d is here. Sigma and omega d. The problem here is your locus doesn't cross here. That means you have to change your locus. Your old locus doesn't work because it doesn't cross the design point. So you have to modify this locus here, right? You modify this locus to cross this point and this point. That's what we have to do. How? By adding a 0 on the left half plane of the S plane using the PD controller. Do you agree with me? Or does it make sense? Make sense? Okay. So we have to find the PD controller now. Okay, too many animation. Okay, what do you do? What do you do? How do you design PD controller? So slightly different, this is slightly different from the PI controller design here, right? Because in the PI controller design, we were thinking about putting a pole at the origin and then putting a 0 right next to that origin. So pole 0 cancellation, that's what we did for the PI. PD case is a little different. Let's take a look. From the analysis and the root locus geometry, we want the dominant poles at this point. This point here, S equals negative 3.6 plus minus J 6.17. Now, we want to add the PD controller. This means we want 1, 0. We want 1, 0. And by adding that 1, 0, that total angle, the sum of the 0 angle minus the sum of pole angle has to be 180 degrees. So we go from there. So we have to use the geometry. You have to make sure that you draw the locus. Use the ruler with the graph paper. Do it yourself. And you have to see it, okay? The trend, the geometry, to correctly calculate the angle again. So here we have to determine the location of the PD0 ZC. Z controller, 0 for the controller, okay, ZC. So we have to fulfill this requirement for that point to be on the locus, right? So we use this geometry here again. Theta 1. What was that? Theta 1 was at the origin S plus 4, S plus 6. Remember, we had 3 poles. Then what we do here is to add whatever location we don't know yet, but you add your 0 here. And we have to figure out this location. In order to figure out this location, we use that criteria of this angle. Okay? Again, we have this design point. We want this design point to lie on the new locus. That's what we want to do here. Are you guys with me? Good. Now, okay. The sum of zero, only one zero, ZC, right? The zero for the controller. That's the angle for that. So we want to get this angle. Minus the sum of the whole thing, because whole things here, 1, 2, 3, theta 1, theta 2, theta 3, these are all poles, equals 180 degrees C. And we can get all these angles, 1, 2, 3, right? So let's practice. 180, so theta ZC equals 180 plus the rest. So let's start from theta 1, theta 1. Okay, prepare the calculator. Okay, theta 1. Oh, 0. Okay, and this axis here, that is negative 0.6. Sorry, 3.6. So that is inverse 10. Vertical component is what? 6.17. Lateral component is what? 3.6. Okay. So get me the number. What's that? The angle. Did I calculate myself? What is the angle? Could be 60 something. 69, 59. 59.7, thank you. And from the geometry, that 59.7, you can see that that is this angle. So we have to do what? 180 minus 59.7, which is 120, 120.6 degree. Okay. 6, whatever. Okay. You may be right. Anyway, so that's theta 1. Theta 2. Theta 2. Inverse 10. So this is theta 1. 2 is inverse 10. So numerator is always the same. Denominator. What's the number there? Negative 4. 4 minus 3.6. 4 minus 3.6. That is, that should be 93 point something. No. That is 86.29. In this way, theta 3 should be 68.75. Okay, the same way. You add up everything, you get 455. Oof. Then what? Yeah, 455 means you rotate it once, right? 360 degrees. So 455 minus 360. That's 95.3. So, oh, you got that theta Z sub C. What was that? 95.3 degree. Nice. We got that angle that fulfill the angle requirement for the point over here to lie on the new root locus. Any questions so far? Yeah.
Theta 1, that when we found 59.7, like the first value, you knew that was the wrong value because looking at it, right?
That was this angle. Yeah. Right, but we're looking, okay, you have to 180 minus that one. Yeah. Okay. Any other question? Okay. So now what? Okay, we got the angle. How do you get this location now? Ah, angle. What about the location? Any idea? Any suggestion? What would you do? What would you do? You got the angle. How do you find now the location? You got the angle, okay. What would you do? What would you do? Use a trigonometry. Okay? All right. We know that this angle is 95.3. Use this triangle here. Now say this is your design point, which is this. Is this, okay? And y-axis, 6.17, that is omega d. X-axis, we have to know because we know exactly. So let's say we draw a 90 degrees line below this point. Where does that cross in this axis? With what point? Negative 6.17, right? So this point here should be negative 6.17. This point here should be negative 6.17 in this graph. Is that right? Or is it not right? We need more time to think? Looks like you need more time to think. Yes. Yes. Thank you. Should be negative 3.6, not 6.17. 6.17 is this number, and this, not this C, but this point has to be negative 3.6. Thank you. All right? Okay. You're kind of puzzled because I said some wrong number. Now, this point should be negative 3.6, correct? Okay. So all you need to find is C. As long as you know this C, then you can find the location of the zero, correct? Okay, that's all we need to do. So it's just geometry now, all right? So you follow me so far? Give me one clap. Once again. Okay, someone here. Okay, all right, so by the geometry, tangent, so from this, okay, from this triangle here, tangent 180 minus theta. So this angle here is 180 minus theta z, correct? Because this angle is theta zc. So this angle should be 180 minus theta z, correct? So tangent 180 degree minus theta z equals 6.17 divided by c. Correct? Is it correct? Should I repeat again? This angle here, from this geometry here, we found this theta zc, which was 95.3 degree. Therefore, this angle, which is here in this triangle, should be 180 degree c minus theta zc, right? Right or not? Right? Then, that means tangent. This angle is this x component divided by this y component. So, sorry, y component divided by x. So 6.17 divided by c. So we change this position. You move c here and then tangent component over here. You calculate it. C is 6.17 divided by tangent 84.7 degrees, which is this value, equals 0.57. So C is 0.5724. Okay. What is the now? What is the location of 0? What is the location of the PD compensator 0? Someone. What minus what? What is the now location that we determined from this? What is the location of the PD controller 0? What is it? What minus what? What number minus what number? Or what number plus what number? Zero 0.524 minus 3.6? Do you agree? Yes. So that's your new 0 position. At negative 3.028. That is this position. Huh? So this is, yeah, because this is, we just put it somewhere. We didn't know, right? So 0 is over here. 0.3 negative 3.028. Okay. Okay, if you understand the point that I made so far, please nod once. Once again, only half of you. You did 3 times. That means you understand 3 times more than other people. All right, good. So we got the 0 position, which means we got the PD controller here. Simple. K times S plus 3.028. That is our PD controller. So we put these things together with the original transfer function here. That is this 4-path transfer function, including the controller. We plot the body, not the body, this locus here, and then design point, not the design point, I mean the angle, design angle here, and then this is your new design point, and you can see by adding this 0, the locus has totally changed from the previous one. What was the previous one? Let's go back. Previous one, where was it? Here. That was the previous one. That was the previous locus. Now see how dramatically has it been changed or updated or enhanced. Because you put a 0 here, and this 4, as you increase the k number, it goes to the 0, and these 2 go that way. Okay, it starts from here. As you k is increased, it starts from open loop 4, going to the open loop 0, NZ open loop 0, and then others they approach to each other and then diverge and then goes toward near infinite zeros, up and down. Totally different locus. And then this met the new design point, which is negative 3.6 plus minus 6.17J, where K is 47.2. And of course, this is the down point for overshoot 16%, so that's there. So you have everything. And damping 0.5. Okay. Very good, isn't it? Very good. And the step response, finally. See if we achieved the reduced settling time by 3 times. Okay. Initially, the settling time was 3.47. And with the new design, by adding the PD controller, as opposed to the P controller alone, where K was 43.32, and this PD controller has added a pole at negative S equals negative 3, and K, the new K is 47, which is changed a little bit. Now you have a dramatically changed transient response, which maintains the overshoot, That's changed a little bit, but dramatically reduce the settling time, as you can see. That's how this PD controller performs. Good job, PD controller, right? Okay, question? Any question? No? We move on? Let's have a brain break, 1 minute. Now, again, I'm not going to spend some time to explain this noise thing again, because it is easier to explain and understand when we use this frequency response analysis, which you haven't learned yet. So I am not going to explain, but fact of the matter is that it reduces the noise. For the PD controller can amplify noise signal also. That is one problem with the PD controller. But phase lead controller avoids that problem while achieving the same or similar target. Okay? Thank you. Anyone? So that's your phase lead compensator, which looks almost exactly the same as phase lag compensator, although PZ locations are reversed. That's it. Phase lag case, you put your pole at the origin and then put your zero next to the origin. If you remember, maybe you forgot already. But phase lead controller, you have to choose convenient location for Z, the new zero, and then find the pole position. Okay? It is very similar to the PD design. So the phase lead design is virtually identical to PD design, but since we have this lead pole, not only lead zero, that is only difference. Okay. So what we have to do here is to determine again the point on S plane to satisfy the design constraints. So same as the PD controller. And then we use to determine the angle for compensator, that is also the same. But what is difference here is because your requirement is to meet that the sum of the zeros angle minus the sum of the pole angle equals 180 degrees C, not the degrees, sorry, 180 degrees. Then pay attention to this. Okay, pay attention. Now, to satisfy this, now we have this phase lead controller, which means we have zeros from the lead controller and then poles, well, sorry, A0 and A pole from the lead controller. So we can rewrite this, the sum of system zero angle minus the sum of the system pole angle. Plus, now look at this term. Pay attention here, look at this term. This is the sum, not the sum, only zero, 1, 0. Zero angle, zero lead controller zero, minus lead controller pole. Okay, so actually, so this has just you can put it here. For example, you can decide to put ZC, which is the controller's zero location under the design point, right? So that's 90 degrees, and then you can then determine the PC because we already know 90 degrees and we know other angles. Okay, that's one. Or you can put this ZC overlaps with other poles from the system so that there is a pole zero cancellation. Okay, so almost exactly same as you do the PD control, but we have one more pole, so you have to consider that. The only thing to do is to decide this zero location first. That's the only thing, okay? Because you have pole and zero, not just zero. And to do that, pro tip, number one, you can put the zero right underneath of the design point. If this is negative 3.6, your zero is negative 3.6. That's what you just determined. And you don't put these poles and zeros from lead compensator close to the axis. It has to be far from that axis, okay? Okay. That's it. That's it for the phase lead compensator. Rest of them is the same, identical. Now let's put it all together in one table. PI controller, improve the steady state error. That's your transfer function, the PI controller, which increases the system type. Error becomes 0, and 0 at negative ZC is small, and active circuits are required. Or you can use phase lag controller, which you improve, not eliminate, but improve the steady state error. Difference here is you have a pole at negative PC, okay? Very small number. And then 0 close to the pole, to this pole, okay? So that pole 0 cancellation occurs here. So that's how you do the lag. So major difference here, active circuits are not required to implement, which I'm gonna show you a little bit later. Now, PD control, which we did today, and then lead control, which we did today here. PD controller adds zeros at negative ZC, selected to put design points on root locus. Okay, new design point. So that is a major difference from the PI and lag. Design point not change much. PD lead design point total change in your locus change dramatically. Active circuits required and can cause noise and saturation, but the lead compensator can remove the problem with the noise, and rest of them is similar, but major difference here, you also add a pole, okay? More negative than the 0 location. So that is kind of all these compensators at a glance. Any question? Okay. You can also put together lead lag together. You first perform the lead compensation, then you add another compensator, lag, in series. Okay? See what it does. You cascade lead and lag compensator to address both transient and steady state response. Steps are following. Number 1, you evaluate the uncompensated system to determine the design transient, right? You have to determine a new design point for lead and PD, which we did today. Determine the new design point, then design the lead compensator. You choose convenient Z, right? Like once you have the design point, maybe right under that design point, or find other pole location to pursue the pole 0 cancellation. Then find PC based on the desired criteria. Then simulate and check. Once this is done, then next is to design the lag compensator for the lead compensation system to yield the desired steady state error. So for example, first you work on lead first, always, to address the transient response. But after even using this lead compensation is done, you still have a little bit of steady state error problem. Okay, you add another compensator in series in the block diagram. Okay, so that's what you do. Based on the response and design point, everything, establish it for the lead compensation. First, you find the relationship between Z and P based on the static error constant. You remember that we did last Tuesday. Then you choose PC lag sufficiently close to the origin. So, that P and Z, this 0 poles minimally augment the lead compensated response close to the origin. Then you find Z, okay? So that's how you do the lead lag. Or you can put together PD and PI together. We call that PID compensation. How many heard of you PID before? Yes, a lot, yes, PID, right? So that is simply, you once perform PD, then you perform PI. In the block diagram, they are put together in series. Okay? As like the lead lag compensator, you first perform PD, right? Exactly the same. So evaluate the uncompensated system for the design point and design PD controller, then find the Z location based on the angle criteria. Exactly the same. Okay, you did that. You have this steady state error, and you want to eliminate now the steady state error without touching that transient response, which already fulfilled, already satisfied. You don't want to touch. Then you add another controller after this PD, then you perform the PI. How do we do it? We choose the Z to yield the satisfactory settling time and minimally augment PD compensated response, okay? So you can do that. That's your project too, PID and lead lag, okay? And I heard that project one, the students' score is so high, so TAs were kind of, last year it was 80, now it is 90 something, so something is wrong, or you guys are super smart, so either way, we'll see. Okay. So let's look at the PID compensation. So this is your transfer function of the PID controller. And you rewrite everything. You can see the component KS as KD for the PD controller, and KP, and K times ZZ over S, that is KI component. So PID. Now looking at the block diagram here, so this K is your controller. If K is alone, that is a proportional control. But you add I and D in this case, like this. Looking familiar, isn't it? You saw this from where? This block diagram. From your project. You saw this block diagram, right? Something like this, similar. You remember? Forgot already. Remember, right? Okay, so that's that. And then in the project, one problem asks that, okay, remove KI or KD. So in this case, you remove KD is 0. What happens? And this line is gone, cut, nothing. Then this is PI controller design. Or you remove KI is 0. Then you remove this part, that becomes PD controller. Okay? You did this PI in your project, and then you're asked to remove KI line. So you compared P controller with the PI controller. Remember, right? You did that. Okay? Good. Now, I'm not going to run the video. Please watch this 10-minute video, okay? It's very important, PID system, okay? And then this is bonus slides, which is not an exam. However, it shows this is a op-amp circuit, and it shows what difference when you have the lag compensator or lead compensator, what it means by adding active component, adding energy. See, you add capacitor, something like that, okay? In parallel or in series. So you can find this circuitry for the lead lag compensator in this op-amps, or even without the op-amp. The R become R instead of R, you have CR in parallel or RC in series for different impedances there. Okay, so take a look. Okay, not part of the exam. However, if you were curious about, okay, what do you mean by adding energy in the system, this kind of shows you. Okay, it gives you a little bit of answer there. Another bonus lecture, since we have a little time, I'm not going to go over, but this is about notch filter, which removes certain signal from the system. Okay, so you go over yourself here. So that's about 25 years ago. I worked on designing future space telescope, which is far beyond the current James Webb Space Telescope. I was also involved in designing a James Webb Space Telescope in the very early stage. This was like far, far, far beyond. Okay, so formation flying telescope in space, and this is a 30-meter in diameter mirror, which is very thin. Okay, so long story short, for this, you need micro-actuators, you need control. So for example, so this was a NASA mission, and I was working at NASA's Jet Propulsion Lab in California for about 10 years. I got a phone call from a strange person. It was a scientist with an agency. Have you heard of National Reconnaissance Office, NRO? Oh, it's an agency. This is a reconnaissance from space. So you have spy satellite, and then basically all these spicing from space. That's the agency. So one of the scientists working there called me. Oh, we are kind of having this space telescope design, ultra-large space telescope design. So you look up, that's NASA mission. You look down, there is a spy mission. Because you have Earth, you have this spy satellite, low orbit. One goes and then, have this shot, but since this move fast, you have to move out, and then you have blackout period for 20 minutes or 12 minutes, whatever, 6 minutes, whatever, until next one arrives. So I have to wait for the next one, right? So you have that blackout period, and something important thing can happen. What if you put your ultra-large space telescope mirror at the geostationary orbit, where your GPS satellite stays? Once you put that in here, it stays there. As Earth rotates, this rotates together. So it looks at just one point. So it's 25 years ago, so it was a Saddam Hussein. You want to look at Saddam Hussein, just for example, right? So that's one of the kind of design. Of course, this is a basic research, right? Otherwise, I have to kill you if I tell you, right? So it's basic research. So we are looking at a bunch of micro-actuators. Oh, you're the expert, so can you give us kind of a proof of concept design and some demonstration? Oh, yeah. So we got small money received from the National Reconnaissance Office. And then after that, few agency calls, so I was responding. So I got this funding from this agency for a few years. Long story short, these micro-actuators, these are a scanning microscope image. The size of this is 1 micron. So, thickness of your hair, what is it? Do you know? It's 50 to 100 microns. So if your thick hair is about 100 microns, 0.1 millimeter, this is 1 micron. So see the size? That's why you cannot see anything over there. Because it's beyond 1 micron, the visible light wavelengths cannot resolve it anymore. Okay, so beyond this, you cannot even see if you want to see it. So you have to use electrons instead of photons. Anyway, so these are complex structure. I don't have time to explain, or this is beyond, and this is nothing to do with this class. However, you put together this, anyway, what you're looking at this is this. So you had this professional photographer with the very expensive camera and then took this shot. So that's what you're looking at. Don't spend too much time because we have several of your classmates, okay? So you have this bunch of these actuators. These are called CompDrive actuators, CompDrive, and you apply voltage, AC, then it moves like this because the electrostatic force, okay? And as it does, and there's a bunch of electrostatic actuators, and it opens and closes sequentially, like inchworm, inchworm, so that this moves up and down. And that up and down motion gives. So we did this modeling because we developed this actuators. What you see is kind of old version. This is a new version, and so we how much force it exerts, how much it moves. So based on that, okay, you did modeling. So what is with this exerted force? How much can it move? How much can it be controlled? Okay, so that's kind of what we did. See how much complex PID control will be required for that? Huh? Thousands of actuators. So you have to model each of this. Say we need PID, phase lead, phase lag control. Then you combine thousands of this cross-linked through this truss structure, and then you put this mirror on top. See how complex is the system, right, in terms of the control. That is ultimate control challenge. Okay, so that was what was happening 20 years ago, and I happened to leave the place, and I joined here 20 years ago. So I don't work on this anymore. Okay, so that now that's a mirror. So let me quickly go back. Say this is the space mirror, ultra large space telescope. It has to be stabilized, right? It has to be stabilized. It has to be slow, maybe. You don't want to have a vibration that the basically gone. You may disintegrate the system. But if your characteristics, if you plot the body, and then this is your step response, not only this low frequency profile, but also you have this high frequency noise. Imagine that is your system, space telescope mirror. $2 billion is gone because of that in space. $2 billion minimum. Okay. James Webb, we costed $10 billion from the development to launch. $10 billion. Okay. How do you solve this problem? You may have to, this may be okay, also this could be controllable, but what about this? This has to be removed. So that's where notch filter comes. So for example, this is your original system, which gives this transient response, and then this permanent noise problem there, okay? How do you remove that? So now you have poles, complex conjugate poles here, and then you have poles near the imaginary axis, very close to j omega axis. Now we put the notch filter, in which you put zeros very close to these things, okay? So initially, this is your transfer function, and this was dominant, okay? And then you add this notch filter, which is a different form of compensator, not PD, not lead, but notch. This kind of, you remove one specific point of that frequency, okay? Then what happens here, because you put these zeros here, your roots move from x to 0. Therefore, compare this original step response and notched step response. You remove this vibration. Very, very important problem. All right? Done. Any question? Question? Yeah. So actuator, so my background is MEMS. It is a micro-electromechanical system. It's a new, right now is not new anymore. The 30 years ago it was developed. So that time was brand new. So it is a totally new way of fabricating microstructures and actuators. It takes a little time to explain. But ask Google, MEMS, what is it? How is it done?